In this video, we'll finish up our graphing chapter by discussing some other types of graphs that you'll sometimes see. Some of these graphs include bar graphs, Pareto charts, pie charts, stem plots, and time series graphs. I should mention that these first two are just different versions of a histogram that we would do with continuous data, but in the bar graph and the Pareto chart, this is the qualitative version, or what we would do with categorical variables. So for a bar graph, it's the exact same idea as a histogram, where the heights and lengths represent the frequencies of the data. However, in your bars, what you're going to notice is that the bars are going to be separated, and normally in a plot you'll either color code them, as on a computer we're doing here, or you'll have a label underneath each one indicating the different cities: Atlanta, Baltimore, Chicago, St. Louis, and Washington, and the number of homelessness in these different cities. So for these bar graphs, you're going to start with your traditional frequency chart for categorical data, and then you're going to just write your bars in the particular heights. Note that because categorical data don't come in any particular order, these bars don't have to go in any particular heights for a traditional bar graph. So consider, what's the difference between a bar chart and a histogram? Looking back at this bar chart, the big difference that I hope jumps out to you, first of all, is in the x-axis, where we still have the label of the variable that we're talking about, but instead of having all of the different tick marks down here, we would have a single tick mark per bar, kind of right in the middle. So that it would look more like a midpoint, but we're still drawing bars around it. So we'd have a single tick point, and then we'd write Atlanta underneath. A single tick point, we'd write Baltimore. Single tick point, we'd write Chicago. Single tick point, we'd write St. Louis. A single tick point, and we'd write Washington. So that's one big difference between a bar chart and a histogram. The second big difference between a bar chart and a histogram is a little bit more subtle, but it involves the space between the bars. When we have space between the bars, what we're saying is that there isn't a connection between these bars necessarily, especially when we don't have a continuous x-axis. What instead we're saying is that each of these bars are categorical. And again, with categorical data, this is an important and a good thing to do. What we want to make sure of is that when we're graphing quantitative data or continuous data, that we don't have a space between the bars, because in quantitative data, it is continuous. So where this comes into play again is with the space, where we really want there to be a space when we're dealing with qualitative data or with categorical data, and we really don't want there to be a space with quantitative data or numerical data. Thus, the bar chart is going to be primarily differentiated from the histogram, because a bar chart is going to have spaces between the bars, whereas a histogram will have no spaces between the bars. Wink, wink, nudge, nudge. Sounds like a great test question. A Pareto chart is just a bar graph with the columns arranged from largest to smallest. So again, we mentioned that there's no nice way to order these columns necessarily in a bar chart. It doesn't really matter. However, in a Pareto chart, what you're going to do is you're going to take these columns and you're going to arrange them from largest to smallest. So we'd arrange it in the order Atlanta, Chicago, Washington, Baltimore, St. Louis, as opposed to just having it in this random arrangement as it is here. Note that just like the ogive is kind of a definitional thing, the ogive is a a cumulative frequency polygon. The Pareto chart is kind of the definitional thing in graphing categorical data. The Pareto chart is just a bar graph with the columns arranged from largest to smallest. So it really is a definitional thing, something for you to learn and memorize. Another common type of chart is a pie chart. This is a circle that's just divided into wedges according to the percentages or the relative frequencies of each category. So for example, we would break up our circle into little slices that represent the different percentages. Note that in a pie chart, if you're drawing it by hand, it's important to be roughly accurate to about 1/8 of the pie. So a quarter of the pie is 25%, and then if you cut a quarter in half, that's 1/8 of the pie. That 1/8 of the pie is about 12%. So if your graph is correct to about 1/8 of a pie, then that tends to be good enough for me in terms of grading. So about Baltimore's size slice. If you're close to within that range, you're good for me. With the pie chart, what we want to emphasize is that certain pie slices are larger or smaller than other pie slices. So in a pie chart, the emphasis is going to be that Atlanta has a higher percentage than Washington does, then Atlanta should have a higher slice of the pie than Washington does. So the pie chart is all about demonstrating the size of the different pie slices. So those are our two plots for our categorical data. There's another couple types of plots that we didn't talk about that are a little bit more basic and not as often used in real data analysis, quite frankly. One is the stem plot, and you've probably heard of the stem and leaf plot in your previous courses, in a high school math class or something like that. The stem and leaf plot represents quantitative data by separating each number into two parts. The stem, which is typically the digit on the very left side, and the leaf, which tends to be the right side digit. So for instance, we may have this data, two-digit data, where we have the stems being the entries on the left and the leaves being the entries on the right. So the stem is going to be 5, 8, 7, 5, 6, 7, 8, 6, 6, 6, 7. Now how a stem and leaf plot tends to be constructed is we write all of the stems in order on the left. So we'd write 5, 6, 7, 8, and then a vertical line. And then on the right side, we add all of the leaves in numerical order. So we have the 50s place in this particular data set, and then we would write all of the numbers that come in the ones place. So we've got a 4, and an 8 after 50 in this data set. Next we would move on to 60s, and then we would write all of the numbers that come in the one place after a 6. So numbers starting with a 6. We've got 6, 6, got 6, 7, 6, 5, and 6, 2. Now we write them in ascending order, so it goes 2, 5, 6, and 7 would be how we organize this information. The next value would start with a 7, so this is the next stem. And then we have 7, 8, so that's 1, 7, 5, and 7, 9. So there's 3 numbers that start with a 7, and again we write them in ascending order. So we start with the 5, 8, and 9 we write on the right hand side. This is a great way in which you can visualize numeric information. However, honestly, it's not particularly commonly done with real data sets. One of the reasons why is that this is a great visualization technique when the number of data points is relatively small, but as your data points increase, specifically once we get into things like tens of thousands or hundreds of thousands of data points, this simply becomes an inefficient method for describing your data values. Instead, we tend to use the graphics that we spent more time on, such as the histogram or the frequency polygon. The final type of graph that we'll discuss in this class is a time series graph. A time series graph represents data that occurs over time. So it's important, all of these other data, they can either be quantitative or qualitative. But in a time series graph, this requires that your data aren't just quantitative or qualitative, but that your data occur over a specific period of time. So for instance, the following dataset describes the number of workplace homicides in the year from 2003 to 2008. So here we've got these different numbers, but the data or the grouping variable is by year. Now this is different than any of the other class variables that we had in our frequencies, that we had in the bar charts that we talked about earlier today. All of these occur by year, and we have to have that for it to be a time series graph. So this is a very limited use type of graphic, but when it does happen, like when we do have classes that are over time, this can be a very, very, very useful graphic. So it's limited because we can't use it particularly often, but when we can use it, it's a really good one. In a time series graph, we kind of use the years like our midpoints in the frequency polygon, so those become the entries in the x-axis, and then our frequencies become the heights. So in this place, again, just like a frequency polygon, our years become the midpoints in a sense, and then the frequencies become the heights. This is so useful because it lets us see trends over time and to get a visual of what the data look like and what the frequencies look like over time. Just like how we could have a relative frequency histogram and a relative frequency polygon, we can also have a relative frequency time series graph. Actually, we could even have a cumulative frequency time series graph where the 2004 numbers are both the numbers in 2004 and the numbers in 2003. The 2005 numbers are both the numbers in 2005 and all of the numbers that come before it. So we could do a relative frequency time series graph or a cumulative frequency time series graph. And this actually ends our discussion in Chapter 2 on summarizing and graphing data. Don't forget after this lecture to go on and jump on, do your journal. Again, let me know what you're thinking, what's been helpful, what you'd like to see improved, and then let me know if you learned anything. I'd love to hear what's new for you, what's review, etc. In the next chapter, we'll talk about data description. So this chapter has been all about how we summarize data in terms of tables and graphics. The next chapter, we're going to jump into numerical descriptions of data, such as measures of central tendency and measures of variation.